so far. And this is the part that I will, something that I will repeat on and on of this. Okay, so series of positive sequence. You have integral test. For which from integral test, you know that P series, that is, okay, starting from say 1. That's convergent, or P bigger than 1, divergent, and P less than 1. Okay, and you have the comparison test. So this is what you call regular comparison test. Okay, so in fact, this is one of the most useful thing, comparison test. And then last time we had also what we call limit comparison test. These two are most useful thing about the checking convergence of a series. Okay. I'll repeat this limit comparison test. Okay, before we start with the another one. So our benchmark always is this one here, P series. So the benchmark is the P series. So you're comparing to always, almost always to the P series. Okay. So let's see. Couldn't see this. Example. Limit comparison is this one here. So you're comparing two series, AN and BN, whatever. Right. All right. So this is the one. Compute this one here. What you compute is this limit, AN over BN. Okay. First, if, oh, suppose this is L. If L is positive and finite, okay, then meaning that this is just a number, 2 or 10 or whatever, that means if AN converges and BN also converges. Likewise, the divergence. So, okay, so you have of the same convergence. What I mean by convergence is that it may converge or diverge simultaneously. Are both, or both divergent. Okay. If L is infinity, or what I write something, or just small first. Okay. If L is small, right? So Bn much larger than An. And if the larger one converge, then the smaller one also converge. Okay. I can't say anything if B and diverge. Okay, less than divergent, we don't know yet. If L is infinity is large, L is large means A is much larger than B. Okay, so the smaller one diverge, then the bigger one also diverges. Okay, so that's the basic idea. Another example. Okay, so pick up some problem from the book. There is ordinary comparison test and regular comparison tests. We pick up something. Let's see. Where is that thing? Okay. Uh, 17, for example. Let's see. 17. There we go. So let's put this way here. So this is our AN. Okay, so AN is 4n cubed plus 3n over n fifth minus 4n squared plus 1. Okay. All right. So in comparison tests, before you even start, you got to have a kind of feel. Where would you want to go? Are you going to for convergence or divergence? Okay. And for polynomial, over polynomial or rational function like this, that's easy because what we see is that, well, the top is cubic, the bottom is a quintic, so power of 5. So this should be something like 1 over n squared, right? Okay, so this is what we compare to. We use a b, use b as this one, okay? Because we know that this is, sorry, this one converges because this is p series. If p equals 2, bigger than 1, all right? So this converge. So that's why we compare this to this one here. So an and over bn, let's compute this one. So this gives you 4n cubed fifth minus 4n plus 1 times divide by this. So we find, okay, so you're dividing by this one. So you see here that the you have n square over, okay, so this is the power 5 now, and it's power 5 also. So this gives you the limit is 0. Sorry, limit is 4. And goes to infinity by limit. Okay, so by limit comparison test, we are in the first, I mean, first case here. So the convergence are the same. Okay, and because we know this sigma bn, sum bn this that converge, then an must converge also. Limit comparison. This, yeah, whatever. And from 3, 1, this converge. Okay. All right. So one reason why we prefer using comparison or limit comparison tests, because we don't need to compute much. Okay, so there's not much computations. Just being able to compare with something that we feel that is appropriate to. Now the difficult thing is that find that comparison. Okay. All right. So that's limit comparison. Let's see now the what we call the, I think the fourth. Sorry, did I see record already?
Yes. I think you have, sir.
Yes. Right, good. So the fourth one is what we call a ratio test. All right. So even though the two of the most useful things is the comparison, that means you need to find, uh, say, a benchmark. Okay. Um, the easy thing about ratio tests is that you don't have to find a comparison. So for, let me just take a note. Yeah. Test, limit comparison test. So benchmark. So in choosing a benchmark, then you should know before we checking the convergence, whether you're aiming at convergence or divergence. Convergence. Divergence. Then you can choose a benchmark accordingly. If you're aiming for convergence, then you choose something that converge. Right? If you feel that what you're having is the divergence, then you choose something that diverges. All right. So this is the problem of choosing the benchmark. Okay. And the benchmark is almost always the P series. So benchmark usually almost always P series. Then you have to choose P bigger than 1 or P less than 1. So that's the problem. Okay. Okay, so the fourth one, something that make it slightly easier because you don't have to find benchmark. Is what we call the ratio test. Okay, so you're given a series. Of course, this is still positive terms. Okay. Then you try to compute this one here. Uh, Rho equals to limit of um, this limit. The ratio of two consecutive terms. Limit of two consecutive terms. Okay. Then you don't have to find B, a comparison. Okay. So you compare and to and itself. Okay. So this is the conclusions. One, if um, the all right, if rho is less than 1, okay, then let's convert this. Okay. If rho is bigger than 1, then diverges. It's a good thing because you know the case where it converges or if you diverges also. Divergent. All right. And the third one, this is the critical thing, is that if P is this is 1, then there's no conclusion from this test. Okay. So let's see. Um, Example here. Just like just a note here. Okay. If uh, if uh, for a geometric series is always something that looks like this one. Uh, okay, so let's see. What is this is AN. Okay, so if you compute two consecutive terms, you always get this one. Okay. So in this case, rho is, that's why this is similar to this one. This is rho in Greek. This is R. Okay, so meaning both are radius. Okay. So this is R. Okay. And we know this uh, for geometric series. So the constant. So rho here is the convergence. Okay. So for geometric series, rho is constant. All right. Therefore, um, let's see what I'm saying. Rho is constant. All right. So by this one, only depending on this, the value for rho. Okay. And for a geometric series, you know that this is converge if rho is, so write down this is R equals rho is divergent for rho bigger than 1. Okay. So in this sense, this ratio test is pretty much looks like uh, a geometric series. Okay, so that's why this is, I would say, see the conclusion is almost the same. See, converge if uh, rho is a less than 1, diverge for rho bigger than 1. The only difference is this one here. This is the critical thing, critical case. See. All right, examples. Okay. So let's put this one here. Okay. So if you deal with this kind of term, exponential or factorial, then it is an indication that you should use the ratio test, right? So here, so the question is about the convergence. Okay. Here, an is 2 to the n over n factorial. Okay, so if we compute this nth plus 1 term, so it's n plus 1 over n factorial, and divides by, see? So let me just compute this way. N factorial. All right, there's something nice here is that you have a lot of cancellations. 2 to the n, cancel this one. So remaining 2 remains 2. And here you have n factorial. We call that this n plus 1 factorial means n factorial times n plus 1. So you cancel the n factorial. So leaving you with just n plus 1. Okay. Of course, if you take limit, so n goes to infinity, so n large, then this goes to 0. Okay. And by this test, the ratio test, 0, so we're in the, oh, right. So we're in the first case where you have convergence. by ratio test. Sequence, the series, which is okay. So on the other hand, if you have um, let's see, is example, yes. Okay, problem 30, for example. This is concrete results. Uh, let's check this one here, 31. 31. Okay. All right, so AN here is, uh, well, this is 2 to the n factorial. Okay, so in this case, AN plus 1 would be n plus 1 times, not times, but power. This is 2 times n plus 1 factorial. Okay, so let's simplify this a little bit here. So we can take the comparison, the ratio. Here we have, so this is n plus 1 power n, right? Times n plus 1. Okay, and you have this one here. So you have, this is 2n plus 2 factorial. So 2n plus 2 is 2n times 2n plus 1 times 2n plus 2. So that's n, yeah, 2n plus 1, 2n plus 2. All right. Okay, so this ratio, we can write this down, n plus 1 times n plus 1, right? Divides to n factorial, sorry, it should be a parentheses, 2n plus 1, 2n plus 2. Okay, so then divides by an, so multiply by 1 over 8. 1 over an is this 2n factorial over n, sorry, n to the n. Okay, so what we have here so far. Okay, and let's see what's cancel. This cancel. Okay, and what we have here is that, let's see, this is n plus 1. So I would say this and this. and not cancel, but you can simplify by power n. Okay, because they have the same power, and then n plus 1, right? And divides by, oh, sorry, let me write this down like this. This is 2n plus 1, 2n plus 2. Okay, and we take limit. Take limit. This n plus 1 is just this limit, n plus 1 over n. N plus 2. Okay, so we'll see here. Let's see the second term here. Second term, you have power 1 on the top and power 2 because you have square denominator. So this goes to 0. This is small. Okay. While this one here, all right, this is something that this is, say, this is, this goes to 1. So 1, so it is a, not in proper word, indeterminate form. Okay. So that's to remind you how to compute this one. You compute the Ln, of course, because this is the okay. So what you compute is actually this n times Ln of okay, and because this is the form of the form, this is limit 0, this is to infinity. Okay, so still indeterminate form. You write this down as this Ln over 1 over n. Okay, and we attempt to use L'Hopital. So we take derivative of this is just, let's see, well, this is equal to 1 plus 1 over n. Make it easier. Okay, so then this is a, and you take derivative. Of course, you change it to x first. Okay, so pretend this is x, not n. Okay, so this is a function. On the top, you have 1 minus, sorry, oh yeah, minus 1 over n square over 1 over this. And well, you have, okay, so this limit here. Okay, and so limit um, is uh, we're done with this n square and times this one is the n square This one. Okay. All right. So you see this cancel. This goes to 1. This goes to, then this is large. So this is going to be large. Going to be large. So by that's the limit. Okay. So the limit. Hoping to get something convergent. Let's see. Times this. Let me check if there is any. Did I make mistake? 1 over n. Okay. So the derivative of this is I think made mistake. I made mistake here. Sorry. This is n plus 1 over n. Okay, and the derivative is just derivative of this 0 minus, oh, okay, sorry, this is the wrong thing. This is wrong. All right, so take derivative. So what we have is 1 over n squared. That's the easy one. Pretend this is h. Take derivative. If just 1 over this, which is 1 over n plus 1 over n, and derivative of this on top. And because this is just 1 plus 1 over n, derivative was 1, 0. And this is just 1 over n squared. Okay, so let's simplify this. Okay, so this is just, all right. So this one cancel this. Okay, so what's left is just limit of, all right, so here, limit of 1 over n plus 1 over n. So this is 1. Okay, sorry. All right, so this is the limit, just 1. And so this limit is just 1, goes to 1. So this limit is 0. Okay, so 0, then we are in the first case of the ratio test. So by, let me just compute, write this down, the conclusions. So by ratio test, uh, series this and to the n over 2n factorial bridges. Okay. So you see this first example and second example. So what's in the term of large? So this in terms of large number, polynomial is the smallest one. Log is actually smallest one, and then polynomial and then exponential. But you see here, even if you make a series of a exponential, but divides by factorial, this still converges. That means factorial is much larger than exponential. See, even with this, I call this super exponential because n to the n. Even for a super exponential, this factorial is still larger than super exponential. Okay, so in terms of growth, what I mean growth, largeness. Okay, so what we have is log. It is still smaller than polynomial, the hierarchy, and bigger than polynomial is exponential. Super exponential is larger than exponential. Okay, but this is still smaller than factorial. Okay, so in the sense that if you divide the left by the right, and it should be equal to zero because that's much something in the right is much larger than on the left. So log over polynomial, that goes to zero. Polynomial over exponential goes to zero. Exponential over factorial goes to zero. Okay, in a sense. All right, questions? All right, now the case of the critical case. Sample 3. Uh, of course, we know this P sequence, LP series. P series. We know this is, again, repeat this. Order. Okay, but if you apply this ratio test, okay, so for example, so in this case, an plus 1 would be 1 over k plus 1 t, and an is just, let's see, of course this one an. Okay, so when you compute the ratio, sorry, n plus, okay. So what you get is that np over n plus 1 to the p. So what you have is n over, okay, so this goes to 0 and to 1, right? This is constant, right? This goes to 1, this is constant, and then this goes to, what this goes to 1. All right, And see this, that's depend on the P. P greater than 1 is convergent. Okay, so this is the critical case of the ratio test. No conclusion from ratio tests. Okay, so ratio test doesn't tell you anything if the limit is 1. Okay, because if you apply it to this case, well, it might converge, it may diverge. So this is the critical case. All right, so this is the drawback of a ratio test, because you have a kind of a hole when you don't have any conclusion from the test. And then you need to check with another test. Okay, questions? All right. I guess the first thing that I forget to mention is this one here. It should be uh, on the nth term your test, meaning that the if a series converges, then the terms must go to 0. And the converse is not correct, is not true. So not say true. Okay, that means if you have a if this limit is 0, then uh, conclusions or convergence of the series. Okay. Example is this. Okay. So this is 1 plus 1/2, 1/3, 1/4. That's right. Okay. Uh, this one you see that the so here en is 1, and of course this goes to 0. Okay, but this is a P series with P equals 1. Okay, so this is the conclusions divergence. Okay, so this is the example when you have the term of this the series gets smaller and smaller, goes to 0, but then the series um, is divergent. Okay, so if divergent, then here's the divergence. Okay, but the divergence goes very slow. Okay, so just an illustration here. Uh, but goes to very slow. But I mean slow. Okay. All right. So let's see here. Uh, Goes to infinity means it is unbounded. So this unbounded means that if you pick any numbers, any big, okay, and then you can find any m positive, you can find m such that this sum from this, okay, so this is finite sum, larger than m, so exceed m for n. Okay, so we'll check this one here, right? So you see, by integral tests, this is basically integral from 1 to n of dx over x. Okay, so then this gives you, this is ln. So ln, okay. So if you like this to be larger than m, then you just pick up, solve this one here. So let's see, apply exponential. So n must be larger than m. Okay, so we choose n larger than e to the m. For example, uh, if you want to use for example, if we choose we didn't pick any number. Okay. Find for example 1 over dot 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 until 1 over n, so that this will exceed 10, for example. Okay, see, from this, then we can choose that n must be larger than e to the 10. So you compute what is e to the 10. So e to the 10 is, let's see, pick 3 is a probably around more than 1,000. Let's see. This is 2.7, 2.7, 3, 3, 2, 2, 5. More than 10,000. Okay. That means um, this divergence is getting larger and larger. That goes very slow. Okay, it's going to infinity, but grows very small. Okay. All right. So just give you an idea for the growth and decay. All right. We'll take a break for about 5 minutes. Okay. Uh, Stop the share and then stop recording. So.